our next subsection is titled Sampling Distributions. This may be the most important section of our entire course, because this section is going to lay the groundwork for how we can actually do the inference part of our diagram. And this is one of the biggest components of all of statistics, is to be able to make an inference from the sample to the population. After we get done with this particular subsection, pretty much for the rest of the course, we're going to be using these results so that we can do this inference. Okay, so let's suppose we have y1, y2, down to yn as random variables representing a random sample from a population with a particular probability distribution, where we don't know what probability distribution characterizes that population. It's actually going to be okay for us if we don't know that, and you'll see why shortly. Also, suppose each random variable has the same population mean, mu, and a population variance, sigma squared. So what does this mean then? So if each random variable has the same population mean, that means the expected value of y1 is equal to mu. The expected value of y2 is equal to mu, and so on. In a similar manner, each random variable is going to have the same variance. The variance of y1 is sigma squared. The variance of y2 is going to be sigma squared, and so on. This is reasonable because we are sampling from the same population. Now, just to make sure you understand what these symbols mean, this mu is going to be an actual numerical value. It could be, let's say, 2.8571. Sigma squared could be 0.4082. And we're going to actually use those values later on when we talk about a GPA example, where maybe our population represents all college students on campus, and we're interested in eventually estimating their mean GPA, where beforehand we might not necessarily know what that is. And what this is saying is that when we take this sample of students, which we will examine, then we know that since each of these students come from the same population, their corresponding expected values will be exactly the same. Now, the random sample part of our discussion then corresponds to the fact that y1 through yn are all independent random variables, and that's going to be very important to us. Now, again, just to emphasize the point, while I am saying that each of these random variables have the same mean, the same variance, and I actually put particular numbers here for them, before we actually take the sample, we wouldn't necessarily know what those numerical values are. The whole goal of statistics basically is to take the sample from the population and then make inferences or judgments about the population. I'm just stating these numerical values here as a way to help you see, what's going on, that in fact each of these individuals have the same mean, same variance. Okay, let's move on. So, questions. Is capital Y bar a random variable? Well, notice that it's actually the sum of random variables, and then we, of course, multiply by 1 over n. And so, yes, it is a random variable. And what that means is that for one random sample size n, I could get a particular sample mean. For another random sample size n, I could get another sample mean, and so on. And because of that, since it's a random variable, as you will see shortly, we can actually quantify that variability from one sample to the next through a probability distribution. Next question. Is little y bar a random variable? And the answer is no. And we do want to make sure that we differentiate from the capital to the lowercase letter. What little y bar here, or lowercase y bar, is represented as one particular value that we got from a sample. And it's just a symbolic way to denote that. So maybe I went out and took a sample and y bar was 2.8 for the GPA example. Maybe it was 3.0. It's just a way to, again, symbolically denote what we would actually get from the sample. Now, what would we expect the sample mean to be on average if we, let's say, repeatedly took random samples of size n from this population, calculate y bar every single time for every single sample? Well, what would we expect that y bar to be on average? Well, in other words, you're saying, well, what's the expected value of my random variable y bar? Well, one can show, and we will mathematically prove this shortly, it's equal to mu. So that's kind of a good thing to have happen. That what would I expect this y bar to be on average? Well, it's going to be what I want to estimate, mu. But also we like to be able to know as well, we know that y bar is going to vary from sample to sample to sample. Could we quantify that amount of variation? And the answer is yes. The variance of y bar, in other words, the expected value of the quantity, y bar minus mu, of course, that would be expected value y bar here, squared, just how we've done a variance in the past. That variance of y bar can be shown to be sigma squared divided by n. Note the role the sample size plays here. So let's say I was taking samples of size of 10 relative to this GPA example. Maybe one time I observe a y bar 2.8. The next time y bar equals 3.2. Maybe the next time I get maybe 2.75 and so on. So you can see there's going to be variability there. But let's say I took a sample of size of 1,000. Now maybe my y bar is 2.95. Maybe the next time I take a sample it's 3.02. Maybe the next time it's 2.98. Notice how the variability in these y bars is much less. Why? It's because of that right there, that n. And hopefully that makes some intuitive sense that if I take a larger sample, my sample is going to reflect that population better just because it's larger. And if I compare, let's say, one sample mean to the next with that larger sample, well, I would expect, since my samples represents that population better, I would expect less variability, less spread, less of a range of these y bars by taking the larger sample than if I had a smaller sample, which is not going to be as representative of that population. We can also think of our standard deviation as well. Again, the positive square root of the variance. The standard deviation is sigma divided by the square root of n. Okay. So let's look at some proofs of why these results hold. And what these proofs rely on, I should say, is what we've discussed in the past. So in the past, if you remember, we looked at situations where we had, let's say, two independent random variables, x and y. And also we had, let's say, constants a and b. And what we proved was that if I had the expected value of a times x plus b times y, I can bring that expectation through the sum and factor out those constants. In other words, this is equal to a times expected value of x plus b times expected value of y. Also, what we've seen before is that if I look at the variance of a times x plus b times y, what ends up happening is that I can bring that variance through to the random variables and factor out the constants but square them. But also, notice since these are independent random variables, I do not have a covariance term at all. Okay, so let's apply the results now to this particular situation where I want to find the expected value of y bar. So another way that I could write this out would be to take the expected value of 1 over n times y1 plus 1 over n times y2, and I keep on going down to a very general nth one, you could say. Look how that matches what we had right here. A and b were constants. Our constants in this case is 1 over n. Instead of just having two random variables, x and y, I have n random variables. So what that means then is here I can bring my expectation through the sum and factor out the corresponding constant as well each time. Now, each of these random variables have an expected value of mu. So, page down here a little bit. That means I have 1 over n times mu plus 1 over n times mu plus, it should have had a ... there, 1 over n times mu. So I could then, let's say, factor out that 1 over n. I have mu plus all the way down to mu. How many mu's do I have? N of them. So 1 over n times n mu, n's cancel out. I'm left with just mu. Now, if you're comfortable then working with summations, you can see how it's a lot less messier. And we get then the corresponding same result. Well, let's talk about the variance of y bar. We can do the same thing. So I have the variance of 1 over n times y1 plus, and I won't show the second one. I'll go all the way down to the nth. Okay. We have the constants, 1 over n. We have the random variables, y1 through yn, and they're all independent because of that random sample. So what that means then is that I can take this as 1 over n squared times the variance of y1 plus ... plus 1 over n squared times the variance of yn. Remember, each of these variances of these random variables are exactly the same. It's equal to sigma squared. So now I have 1 over n squared times sigma squared plus ... 1 over n squared times sigma squared. How many sigma squares do I have? Well, I have n of them. So if I were to sum all this stuff up, what do I get in the end? 1 over n times sigma squared. Oops. And there we go. So this is a very important result, because before we take the sample, we know what I expect y bar to be on average and what I expect the variance to be as well. And if I also want to control the variability of possible values of y bar, what should I do? Well, take as large of a sample as I can, because that will lower my variance of y bar. But this result that we're talking about now with y bar gets even better. One can show that the probability distribution itself of y bar is approximately a normal distribution, where the mean of that for that corresponding random variable is mu, the variance is sigma squared divided by n. This works if your sample size is large. The result here that we're talking about is what's referred to as the central limit theorem, which is one of the most important parts of statistics. It comes in very, very useful in so many different places. While we are talking about this with respect to y bar, this central limit theorem can be actually applied in other situations. We'll look at a few of them later in the semester, but there are many other situations where this works out. Now, so y bar itself, our statistic, which is a random variable, has a probability distribution associated with it. Since y bar itself results from sampling, taking a random sample, because it's a sample mean, people often refer to the probability distribution of y bar, or any statistic in fact, as a sampling distribution. Don't get confused by the name. It's just another name to represent a probability distribution, but a probability distribution for a statistic. So this all works out if my sample is large. What does large mean? Well, a general rule of thumb is a sample size of greater than or equal to 30 when we're dealing with y bar. But this can work out even if you have a smaller sample than that. Just in a general sense, for all situations, as long as you have a sample size of greater than or equal to 30, this tends to work out very, very well in terms of y bar being its probability distribution being approximated by a normal distribution. For emphasis, this whole result here is not dependent upon at all what the probability distribution is for the population. So I don't need to know that. Instead, I can work with like a sample mean, and I have an idea of what probabilities are associated with that sample mean. A very, very powerful result. Now, very often when the central limit theorem is introduced to students, it's introduced instead in this form right here, where I take y bar minus mu, divide by sigma divided by square root of n, set that equal to z, and z now has a standard normal distribution for a large sample. Well, why? Well, this goes back to what we saw when we were dealing with normal distribution, where if I have a random variable y, where the expected value of y is mu, the standard deviation for y is sigma, we can take y minus mu over sigma, that transformation, call that z, and now I have a standard normal random variable. We saw why that was true. And basically, we're just applying this result here. Instead, though, well, what's that standard deviation of y? Well, it's sigma divided by square root of n. So that's why you see that there instead. We will actually use this format here later in the semester so that we can derive some more quantities that are going to be extremely useful for us when we do inference. Now, there is one problem, though, with the central limit theorem, is that notice you have mu in there, you have sigma in there, or, you know, when you say y bar has an approximate normal distribution with mean mu and variance sigma squared divided by n, you have these unknown quantities in there. We will talk about how to deal with that later in this course. Okay, so let's take a look at an example. So this goes back to an example that we've kind of seen before, dealing with GPAs. And let's say that y is a random variable representing GPA. And let's say that we happen to know what that population probability distribution is. And it looks like this. 15 divided by 2,048 times y to the fourth times 4 minus y. And this is for GPAs between 0 and 4. Of course, you can't have a GPA that's not between 0 and 4 in college, so f of y is equal to 0 otherwise. Now, for this particular PDF, one can show, and make sure you can do this, that the expected value of y is 2.86, and the variance of y is 0.4082. Here's what a plot of the probability distribution looks like. And again, what this is representing is, for example, if I want to know what proportion of the population has GPAs between 3.5 and 4.0, I can find the area underneath that curve. Okay, let me go ahead and erase that. Well, let's say that we want to take a random sample, size 20 from the population. Now what that means is that we have y1 through y20 as our random variables. Each of these random variables has this corresponding probability distribution associated with it because it's coming from the same population. Well, why are we doing this? Why are we stating what this probability distribution is? The reason is because notice this doesn't look like a normal distribution at all. But yet in the end, when we work with y bar, the mean of all those y's, we will get an approximate normal distribution. So stay tuned. Okay. So let's say we take this random sample. So that means all the y's are independent of one another. And we have this y1 through y20 as our random variables. And let's say we repeat this process 1,000 times. Well, we can use a computer to do that. So let me go over here to 10. Okay. So I'm going to set what my mu is. I'm going to set what my sigma squared is. I'm going to set my sample size. I'm going to set a C because I'm going to actually simulate taking these samples. And I want to be able to reproduce my results. And then the next set of code is where I actually take the 1,000 samples of size 20. You are not responsible for how this code works. Rather, you are responsible for what the end result is. And that is, I get a what people would refer to as a matrix that has 1,000 rows of these samples of size 20. So if I look at the first 6 of these rows, so set 1 contains my data, you could say, my random samples. My first random sample, the first individual sample, had a GPA of 3.41. The next person had 2.79. The last person is 3.59. So in other words, this 3.41 is what you could say is the lowercase y sub 1. The 2.79 is the lowercase y sub 2. Then for my second sample, my lowercase y sub 1 is 3.01. My lowercase y sub 2 is 3.15. And you can go all the way down to the 20th as well. Okay, so I have 1,000 samples of size 20 each. Let's go ahead and find the mean for each of those samples. In other words, find the row means for this, what would be referred to as a matrix. So I say row means set 1, and I get back a y bar in return. If I use head of y bar, here are the first 6 of those sample means. So if I were to take the mean of all of these 20 GPAs that I just highlighted, that mean would be 2.96. For my second sample, the mean of all these 20 GPAs is 3.11 approximately. Okay, let me come back here. So what the central limit theorem then says for this problem is that the probability distribution here for these y bars should look like an approximate normal distribution with a mean of mu and a variance of sigma squared. Well, does that occur here? So what I could do is find a histogram of all those y bars. We've done a similar thing before where we had a probability distribution for a population. We took a sample from it, we did a histogram, and we plotted that probability distribution on top of it to relate the two. We do exactly the same thing here. So here's my histogram. And also I plotted the normal distribution with a mean of mu and a variance of sigma squared divided by n. Look what I get. The probability distribution matches pretty well with what the histogram gives us. And do note, again, I'm using samples of size 20. You know, the central limit theorem says, well, as long as you're greater than or equal to 30, you should be okay. Well, we can see here for a sample size of 20, yeah, this works out really well. And again, just to emphasize the point here, the probability distribution for the population is not a normal distribution. We can see that. It's not symmetric, for example. But this all still works out. And so, you know, perhaps I did not know that this was actually what the probability distribution was for the population. And perhaps it was something else. And in fact, this is still going to work. And so that's why the central limit theorem is such a powerful result. If I work with my sample mean, take a large enough sample, I will be able to say the sample mean has an approximate normal probability distribution with it. Well, let's actually find the mean of all those sample means. I get 2.85. Suppose I find the standard deviation of all those sample means. I get 0.13. Well, compare that to what we know this should be based upon our proof before. Mu is equal to 2.8571, and sigma divided by square root of n is 0.1429. And so what this is basically showing us is that the mean of all those sample means, which is like approximating an expected value of y bar, using now 1,000 different y bars, that matches what we would expect approximately. so does the standard deviation. And so this is a nice little illustration of our result that we were having before. I could even go further. Suppose I want to find the probability that y bar is between 3 and 4. Well, using my 1,000 sample means that I have there, I could simply find all my y bars that are less or equal to 4. Remember what R is going to do. It's going to do a logical check. It's going to do a true or false. And then it's going to convert those trues and falses to ones and zeros once math is done with it, like finding the mean. And I do that with all my y bars. Also, I do for y bar less or equal to 3. And what do I get? 0.138. Now, of course, here, because of how the GPAs work, that will actually be 1 in the end. But compare that to if instead I use now the probability distribution for y bar, this normal distribution. So I use methods similar to what we've done before. What do I get? 0.158. And we can see we have a general agreement between these two values there. And that's because of the central limit theorem. Now, of course, in actual reality, you're not going to be able to take 1,000 samples of size 20. And so that's why the central limit theorem is so important here. I can take one sample and use then this corresponding result of the normal distribution. Okay. Let's take a look at another example where this could be useful. And the purpose of this example is to help set us up for later in the semester once we start talking about actually making inferences through things like hypothesis tests and confidence intervals. Okay, so let's say a cereal manufacturer claims that it fills its boxes on average with 24 ounces of cereal. And an FDA official wants to inspect to see if what they claim on their label is actually true. So what the FDA official does, it randomly samples 36 boxes of cereal. And so given that, we want to now apply the central limit theorem here. Let's say that indeed this cereal company is doing everything right. It is putting on average 24 ounces of cereal in every box, perhaps a little bit of a high standard deviation of 2 ounces, but let's just go with this example. So let's assume that this is true, that mu is 24 ounces, sigma's, and also then sigma's 2 ounces. Let's use that and let's find some probabilities with the help of the normal distribution here. A key is, notice I'm saying nothing about the probability distribution for these box fills here. So this is what then the corresponding probability distribution would actually look like for taking samples of size 36. There actually should be a comma there. I don't know how that disappeared. So y bar would have an approximate normal distribution with a mean of 24 and a variance of 2, or let me just make sure, variance of 2 squared divided by 36. In other words, a standard deviation of 2 divided by 6, or 1/3. Here's what the probability distribution will look like. And if I wanted to find a corresponding probability here so that we just get used to this, like the probability y bar is greater than 23, here's 23 here, and so we can see the area underneath that curve then will be quite large. And to find that probability, what I can do is again use the complement as we've done before. Also relate this to a CDF as well. And what do I get? Well, 0.9987 using the p-norm function in R. Well, what's the probability of being between 23 and 25 ounces? So again, through this plot, we can see, oh, that probability should be very, very large. How do I find that probability? Again, think of it in terms of the CDF. This would be the CDF evaluated at 25 minus the CDF evaluated at 23. Use my p-norm function to find that, and we see that this probability is extremely large. Okay, now we get back to this inspector. Suppose the company will be fined if the sample mean weight of the boxes is not within plus or minus 1 ounce of the advertised true mean. What is the approximate probability that the company will receive a fine? Okay, so again, this FDA inspector is maybe going into the manufacturing plant, takes a random sample of 36 boxes. For each of them, he weighs them. How much are they? Now, if the manufacturing process was actually being done correctly, what's the probability that this inspector will say, hey, my sample mean is actually, let's say, 22.5. I'm going to give you a fine. Or maybe 25.5. So what we want to find then is what's the probability that y bar is less than 23 or y bar is greater than 25, because that's when the fine will occur, plus or minus 1 ounce from that 24 ounces. So this is equivalent then to saying, well, 1 minus the probability then that y bar is between 23 and 25. So in other words, I took the complement. We just found that probability is 0.9973. So the probability that a fine will occur is 0.0027. So it's a very, very small probability. So again, this logic here is saying, okay, let's say that this is being done correctly. What's the probability of it being found to be done incorrectly? This kind of logic is going to be used a lot then once we started formally talking about using inference procedures here. Okay, so that's the end of this particular section on sampling distributions. Like I said before, this might be the most important section of this course.